One last thing when we're talking about how it is that things are moving at the sky is timekeeping. So the original people who worried about what time it was were astronomers. And this makes sense because we're the ones who are tracking the motion of the stuff up in the sky, and we tell what time it is by where the stuff is up in the sky. Now, to help us understand how we tell time, we have to define another special location on the celestial sphere. This is the meridian. The meridian is the line that goes from due north through the zenith to due south. Okay, so remember, the zenith is the point that is directly above the observer. So it goes from due north directly overhead to due south of the observer. Now, what this means is that just like the zenith travels with the observer, so does the meridian. Your meridian here is not going to be the same as the meridian in someone in Denver or in Las Vegas or some other part of the Earth. The meridian travels with the observer. Now that we have defined the meridian, we can now define noon. So the way that noon used to be defined, we have now messed around with how it is we define stuff, but back in the day, we used to define noon as the time when the sun was on the meridian. So if you've ever heard the phrase high noon, the way that you can tell that it was noon is because of where the sun is. When the sun is at its highest point in the sky, then it's noon because it travels up, 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 hits the meridian, and then starts going down, down, down again. Okay, so when the sun is at its highest, then it is noon, it is high noon. So noon is when the sun is on the meridian. Now that we know what noon is, we can define an apparent solar day. The apparent solar day is the time it takes from one noon until the next noon. In other words, from the time when the sun is on the meridian until it cycles around the sky and gets back onto the meridian again. This is one apparent solar day. If you've ever kept track of time using a sundial, you're keeping track of the apparent solar day based off of the motion of the sun in the sky. Now, just telling time based off of the sun actually starts to get troublesome. So, one problem that we have is that the Earth orbiting around the sun actually speeds up and slows down. When the Earth is at its closest to the sun, it travels faster, and when it's far from the sun, it actually travels slower. What this means is that when the Earth is traveling faster, it actually has to rotate a little bit more to get the sun back up on the meridian, meaning that that day from one noon to the next noon is a longer amount of time. Then, when the Earth is far from the sun and traveling slower, when the Earth is far from the sun, traveling slower, the Earth doesn't have to rotate as much to get back to noon, so it is less time from one noon to the next noon. Now, something that's kind of interesting, the Earth is actually at its closest to the sun in January and farthest from the sun in July. So, if you ever thought that the reason that the seasons happen is because of the distance of the Earth, that's absolutely not right. Remember, we're in the northern hemisphere, and we have winter in January, and yet we're the closest we get to the sun during that time. So it's all about the tilt of the Earth, or axis for the Earth is what causes seasons. Now, another problem we have with keeping track of time just based off of the sun is that the sun isn't always in the same position of the sky. We've mentioned previously that it drifts north and south, and that's going to then also affect how long it takes for the sun to get back onto the meridian. What all of this means is that one apparent solar day is actually a different amount of time from another apparent solar day. Every apparent solar day is a slightly different amount of time. Now imagine that you're a clockmaker. Try to figure out a clock where every single day is slightly different. Now you can understand some of the headaches that happen when we're trying to keep track of time. So, to avoid the problems that we get from the apparent solar day just tracking the motion of the sun, we have invented what we call the mean sun. What this is the average. What is the average motion of the sun throughout the entire year? Okay, so from the mean sun, we create the mean solar day. This is the average length of the solar days throughout the entire year, and this is the 24 hours that we actually keep. Okay, so the mean solar day is what your watch is keeping track of. The apparent solar day is what a sundial keeps track of. Now, although we have started to keep time the same because we really like to have timepieces to help us understand what's going on, there was still a huge headache. So remember, a meridian is defined based off of the local observer. What this means is that when people were setting up cities, every city had its own local noon. So noon here in Orem is going to be different than noon in Las Vegas, and is going to be different from noon in Denver, and it will actually be slightly different from noon in Salt Lake City. Orem is slightly farther east than Salt Lake. So every single city had their own local noon. Now, when the fastest thing that you had to get from one place to another was a horse, it really didn't matter. It took too long to get from one place to another. You would just reset your watch when you got to the new location and go from there. However, we then invented trains. And trains could go faster and for longer than horses could. So imagine that you're a railroad tycoon and every single city has its own local time. How are you going to set up schedules? Are you going to base it off of the destination? Are you going to set it based off of where the train's leaving from? Are you going to go somewhere in the middle? Or do you define your own local time? This became a huge headache. So to help simplify things, we invented time zones. Hopefully you've heard of time zones before. The general idea of a time zone is that it's this region of the Earth where everywhere in the time zone is defined to have the same time. That 12 o'clock p.m. happens everywhere at the same time within the time zone. Okay, so it used to be based off of a single city within that time zone. Even that has now changed. It is now based off of your distance away from Greenwich, England. So where we live, or at least where most of us live, here in Orem, Utah, is based off of mountain time, which is 7 hours shifted away from Greenwich. So everywhere within this region has noon at the same time. Now, because of the invention of planes and jets and even faster means of travel, I'm kind of starting to get to the opinion that maybe we should actually just go to universal time, where it's the same time everywhere, no matter where you are, and you just change your hours of business based on what makes sense for whether it's day or night. But don't worry, that's probably never going to happen. Nobody in important places actually listened to me. Now, what we've talked about is the solar day. This is what most people care about. We like to be up and doing stuff when the sun's up, and we go to bed when the sun goes down. However, astronomers have another way of keeping track of time, and this is based off of the motion of the stars. Okay, so we have a solar day, which is based on the motion of the sun. We also have a sidereal day, which is based on the motion of the stars. Okay, so sidereal, we're going to see this term a couple of places. This means according to the stars. A sidereal day is a day according to the stars. So what this is the amount of time it takes from when a star is on the meridian until that star cycles around and gets back on the meridian again. Okay, so this is a sidereal day. A sidereal day is actually 4 minutes shorter than the solar day, the mean solar day that we talked about previously. Okay, so a sidereal day is a little bit shorter. Now, the reason for this may seem strange, but the reason for it is because we are orbiting around the sun, which is going to affect how long it takes for the sun to get back on the meridian. The stars are so far away and they are fixed, or at least mostly fixed in our point of view. So, for example, if we're going to define a sidereal day based off of the stars in Cygnus, then the Earth only has to rotate a full 360 degrees. It makes one complete circle. And then the stars in Cygnus are back on the meridian. However, as we define a day, a solar day, as the Earth is rotating, it also moves compared to the sun. So to get the sun back to the same position in the sky, back onto the meridian, the Earth now has to rotate a little bit extra to get the sun back into the same position. It's because as we rotate, we also orbit around the Earth. This extra amount for the Earth to rotate to get the sun back in the same position, that's what then leads to that 4 extra minutes. So because of that, the solar day is slightly longer. Remember this idea that we don't just rotate, we also orbit? That's going to play a part in explaining some other differences to how it is that we define certain times. Okay, we'll talk more about it next time when we talk about the moon. Now, one last piece of timekeeping is the year. The year is not exactly 365 days long. It's actually 365.24 something something something. I don't remember, and it's not really important for what we're talking about. But it is slightly longer than 365 days. What this means is that if you do not take into account that little bit extra part of a day throughout through multiple years, then the seasons and the calendar actually begin to drift away from each other because we don't have this little extra day that's actually part of our year. Okay, well, people realized that this was a problem, so Caesar had it fixed. Okay, so what they did is to make sure that the seasons and the calendar always remained in line. Caesar's people, so Caesar had it done, and his people decided what they needed to do was, one, reset everything, and then from that point on, every 4 years we will add 1 extra day. So these are what we refer to as leap day, and they occur during leap years. Okay, so this helps keep the seasons and the calendar in sync. However, although it's pretty good just adding this 1 extra day, it wasn't a perfect fit. So by the 1500s, the year was actually off by 10 days. Now, 10 days in 1500 years isn't actually that bad, but it was noticeable. So Pope Gregory VIII wanted it fixed. So he had his people work on it, and the first thing they did is they removed 10 days from that year. From October 15th to October 25th did not exist that year. They were gone. Then they revised exactly when leap years are going to occur. So instead of being every 4 years, the new rule is now that we will have leap years that are evenly divisible by 4, not including years that are evenly divisible by 100, unless the year is also evenly divisible by 400. I realize that's kind of long and it's hard to follow through. So because of that, this is why we have flowcharts. Flowcharts make things easier. Okay, so let's take a random day. So let's say the year 1999. Is the year 1999 evenly divisible by 4? No. So the year 1999 was not a leap year. Okay, let's take the year 1996. Okay, so the year 1996, evenly divisible by 4? Yes, it is. Is it evenly divisible by 100? No, it is not. So the year 1996 was a leap year. Now let's do something a little bit trickier. The year 1700. Okay, so is the year 1700 evenly divisible by 4? Yes. Anything that ends in 100 is going to be evenly divisible. So yes. Is 1700 evenly divisible by 100? Again, yes. Yes, it is. Is the year 1700 evenly divisible by 400? No. No, it is not. So the year 1700 was not actually a leap year. Okay, let's do one more. The year 2000. Is 2000 evenly divisible by 4? Yes, it is. Is 2000 evenly divisible by 100? Again, yes. And is 2000 evenly divisible by 400? Again, yes. So the year 2000 was actually a leap year. I hope that this kind of helps you see how it is that we figure these things out. That then leads us to our 5th lecture quiz question. Which of these is a leap year? A, 1995, B, 1900, C, 2015, or D, the year 2020? Go ahead and think about it, and we'll discuss in just a bit. All right, so which one is a leap year? The correct answer is D, the year 2020. Maybe you actually remember it since it just happened a little while ago. Okay, so 95 is not evenly divisible by 4. 2015 is not evenly divisible by 4. 1900 is evenly divisible by 4 and evenly divisible by 100, but is not evenly divisible by 400. Okay, so the correct answer is D. It is evenly divisible by 4 and is not evenly divisible by 100. So the correct answer is D, the year 2020.